construction and working of JFET. Now we would be starting with the junction field effect transistors. So first we have to know what is the construction of a junction field effect transistor. As you can see, in a junction field effect transistor, there are two PN junctions. So the first point is two PN junctions. In this is a N-channel type of junction field effect transistor in which the maximum doping is done with N type of semiconductor. But is similarly, if there is P in the middle, then it would be called a P-channel JFET. So there are two types, that is N-channel JFET and P-channel JFET. The name depends upon which type of semiconductor forms the channel in the field effect transistor. Since there are two PN junctions, therefore there are two depletion regions also. In this depletion region, there are no charge carriers present. In this JFET, the output current depends upon the voltage between the gate and the source. Therefore, VGS controls the current ID or the drain current. Therefore, it is known as a voltage controlled device. And this JFET has three main terminals that are given as drain, gate and source. Drain is a terminal through which the majority of the charge carriers enters the field effect transistor. Gate is a terminal which is doped with the opposite type of impurities. And source S is a terminal through which majority charge carrier enters. So this is the construction of a junction field effect transistor. Now we would be doing the working of junction field effect transistors. We would be doing two cases of the working of junction field effect transistors or JFETs. The case one would be when VGS is equal to 0 and VDS is greater than 0 volt, and the second one would be VGS is less than 0 and VDS as usual is greater than 0 volt. So in case we would always consider N-channel JFET. As in BJT, we had considered NPN transistors for all our characteristics, for our input-output characteristics. In JFETs, we would be using N-channel JFET for the input-output characteristics as well as the transfer characteristics, because electrons flow at a much easier and a faster rate than holes. Therefore, its characteristics can be easily mapped. So, in this, to maintain the condition, the terminals of gate and the source terminals are sorted. So, it both has a potential of 0, and the terminal D and S are connected to a potential VDD, which has a positive polarity towards the drain terminal, and external voltage VDD is connected between the drain terminal and the source terminal. the polarity is maintained in such a way that the positive terminal of the battery is connected to the drain terminal and the negative terminal of the battery is connected to the source terminal. So the current's direction is from drain to source. As we know that in conventional current, the direction of the current is opposite to the direction of the electron flow. Therefore, the electron would be flowing in this direction, in a direction opposite to that the drain current. VDD is applied the charge carriers, that is the electrons, begin to flow from the source to the drain and thus constitutes a current ID or the drain current. But when as VDD is increased, the depletion region increases because the N type is connected to a higher potential, that is VDD, but the P type is connected to a lower potential or zero. Therefore, as the VDD value increases, it becomes reverse biased. Both the PN junctions become reverse biased. But since the potential across the entire N channel is not equal, therefore the depletion region would be formed in such a way that it is bigger at the top, and as it towards the drain terminal it is bigger, and as it goes towards the source its width is smaller. Similar on this side too. This happens because, I will explain this to you. Suppose a potential of 2 volt, VDD is equal to 2 volts. And this is the drain terminal, this is the source terminal. The N channel can be thought of as a combination of any number of resistance. So we are taking suppose 4 resistance. So these are 4 resistance of equal resistance R. Therefore, the equivalent resistance is equal to 4 R. Therefore, after each resistance, the voltage drop would be 0.5 volts. V drop is equal to 4 by 2, 2 by 4, which is equal to 0.5 volts. So, if the potential at D is equal to 2 volts, it would be 1.5 volts after one resistance. It would be 1 volts after the second resistance, and after the third resistance it would be 0.5, and after the fourth resistance it would become 0. Since the potential between VD and Vs is equal to 2 volts. So in this N channel we can write it as 2 volts. It would be 1.5 volts here, it would be 1 volts here, and it would be 0.5 volts here, and it would be 0 here. Therefore, as we go from the drain to the source terminal, we see that the reverse biasing voltage is getting lower. Therefore, the depletion region width would also become lower. Therefore, this justifies the uneven shape of the depletion region thus formed when a potential is applied across the drain and source terminal. If there is no VD provided, or if there is no drain to source voltage, there would be no current ID flowing through the N channel. As we had done before, if VGS is equal to 0 and VDS is greater than 0, that is a positive potential is provided to the drain terminal, and the negative terminal is connected to the source terminal, the since the n type n channel is provided with a higher potential and the p channel a p type semiconductor is provided with a lower voltage, therefore it would have a reverse biasing. Due to this reverse biasing, there would be a depletion region in between the PN junction. The depletion region width would increase in the PN junction. But as we had seen before, that the depletion region width would be more towards the more in the drain terminal, and it would be less in the source terminal, towards the source terminal. But if we keep on increasing the value of VDD or VDS, we would get a certain condition when these depletion region almost touch each other. This condition is known as pinch off, and the potential at which this occurs is known as the pinch off voltage. So when the depletion regions almost touch each other due to the potential VDS provided, this condition is known as pinch off. And the potential at which the potential of VDS at which this condition occurs is known as the potential of VDS is known as the pinch off voltage. After the pinch off condition, initially as the VDS was increased, the drain current or ID was increasing in an ohmic manner. But when the pinch off condition is reached, then the current, then more carriers can't flow through the narrow path. Therefore, all the current density increases, but the current remains constant. So the plot would be ID and VDS. Initially, as the VDS value was being increased, the ID was increasing in a proportional manner. But as soon as we reach the pinch off voltage, that is VP, then the current becomes constant. That is, initially the resistance was a constant value, but when the pinch off condition is reached, the resistance becomes infinity. Initially, as the VDS was being increased, the value of ID was increasing at a constant rate since the resistance was constant. But as soon as it reaches the pinch off voltage or the pinch off condition is reached, that is VDS becomes equal to VP, the current value becomes constant or the drain current becomes constant and the resistance becomes equal to infinity. This current is when the VGS is equal to 0 is known as the IDSS, or IDSS is equal to maximum drain current possible for a JFET. For IDSS, the conditions are VGS is equal to 0 and VDS is equal to greater than the pinch off voltage. We have seen before that if the VDS, that is the potential between the drain and the source terminal, is equal to the pinch off voltage, then the depletion region of both the gate terminals come very close to each other. But they must not touch, because if they touch, then the potential drops. Okay, so what would happen if the VDS is further increased? We must always remember that the depletion region must not overlap each other at any cost. So what happens? The along the length, the depletion region increases. Along the length of the N channel, as we go on increasing the VDS value, the depletion region increases, unless throughout the region, the depletion region, the distance between both the depletion region becomes constant. Then on increasing further, the depletion region enters into a breakdown state and electrons flow at a much faster rate. This is the effect of the increase of voltage from drain to source beyond the pinch off voltage. So what would happen? What would be the effect of this on the drain current? The drain current does not increase further on increasing the VDS, as it has already reached its maximum value. As we had seen before, that on increasing the value of VDS, ID increased, or the drift current increased, or the drain current increased, but when it has already reached the pinch off condition, on further increasing the value of VDS, the drain current does not increase any further, as it has already reached its maximum value. That was before reaching the pinch off condition. Thus, JFET can act as a constant current source when the voltage is between when the voltage between the drain and the source terminal is between the breakdown voltage and is between the pinch off voltage. That is, the VDS must be greater than the pinch off voltage and must be less than the breakdown voltage. Then JFET can act as a constant current source. Now for the second case, that is, now VDS must be greater than 0, and as we had discussed in the previous stage that VGS would be equal to 0, here the VGS is less than 0 or negative potential. That is, at the gate, it is the negative terminal of the battery is connected, and at the source, the positive terminal of the battery is connected. Therefore, the P junctions are the P type of the PN junction is already connected at a lower terminal. Therefore, what would happen at a lower value of VDS, the pinch off condition would reach. So here the gate is connected to the negative terminal of the VGS and the source is connected to the positive terminal of the VGS battery provided. Similarly, here, as we had done in the previous case, that the drain is connected to the positive terminal of VDD and the source is connected to the negative terminal of VDD. So what happens here, that the pinch off condition is reached as at a much earlier state, because the negative or the reverse biasing potential is easily achieved because negative potential is provided at the P junction. Therefore, we reach the pinch off condition or the saturation condition at a much lower value for VDS. Thus, the objective of this negative voltage at gate is to obtain saturation at a lower value of VDS.